Okay, so that pretty much sums up the properties for HCl, but we didn't consider one property. Do you know what that is? It's an acid-base property. We didn't consider, we looked at Bronsted acid-base, right? But there's another acid-base property we didn't look at, Lewis. Lewis, you have to keep in mind that we're totally ignoring Lewis acid-base properties. And they can be important as well. Have you heard of aqua regia before? Aqua regia. Aqua regia is called royal water or king's water. And what it is a mixture of nitric acid and hydrochloric acid. It's a 1-to-3 mix of nitric to hydrochloric. It's yellow, orange, sometimes red fuming liquid. It was named this royal water because it dissolves metals like gold and platinum. Gold and platinum, are they easy to oxidize? No, they're extremely hard to oxidize. Those are called the Nobel metals, coinage. But you can oxidize them. You can get those metals to dissolve by oxidizing. The situation is this. So what do we need? Do we need strong acids? No. You know what's needed? What is the purpose of nitric acid? We'll look at it in terms of platinum. Let's try to dissolve platinum. If we dissolve platinum, what is the nitric acid doing? Is the nitric acid neutralizing the base platinum? Is platinum a base? Platinum metal? No. The nitric acid is not acting as an acid in this reaction. What is this nitric acid acting as in this top reaction here? Take a close look. Yeah, nitric acid is oxidizing platinum to platinum 4. So nitric acid is oxidizing platinum. Now the problem is platinum 4 is unstable. And so what is the purpose of the hydrochloric acid? The purpose of the hydrochloric acid is not as an acid. The purpose of the hydrochloric acid is as a Lewis base, but you're thinking, how can hydrochloric acid, one of the 7 common strong acids, be a base? The hydrochloric acid provides a ready supply of chloride ions, which react with the gold ions to produce this. And it turns out that chloride ions, these are worthless as Bronsted bases, but they're pretty decent as Lewis bases. And so we get another reaction going on here, and this other reaction that's going on here is that the hydrochloric acid, the only purpose for hydrochloric acid is to supply chloride. Why do we need chloride? We need chloride to do this reaction here. This reaction is platinum 4, which is the Lewis acid, reacts with chloride, the Lewis base, to produce this weird anion. This weird anion is called hexachloroplatinate ion. This hexachloroplatinate ion is how we get it to dissolve. And so aqua regia can successfully dissolve gold and platinum. But as I said before, we're skipping Lewis acid base for right now, but it's something that we also have to think about as well to make sure we're comprehensive. All right, so those are the properties of hydrochloric acid. What are the properties of nitric acid? Well, a lot of people say, oh, nitric acid is just a strong acid, but it is a strong acid, true, but it's also a strong what? It's also a strong, where have you seen nitric acid before? Yeah, it's also a strong oxidizer, so be an oxidizer. Does nitrate really participate much in metathesis? No, because all nitrates are soluble. And so it's nitric acid. So if we have something like sodium nitrate, we look at sodium nitrate, what are the properties there of sodium nitrate? So first we look at, well, sodium nitrate consists of sodium ions. So we think about sodium ions. Are sodium ions very reactive? No. For one, I know my experience with sodium ions aren't that reactive. How do I know? Because table salt, you know. It was pretty reactive. I really wouldn't eat this stuff. And so sodium ions are pretty stable. Compared to sodium metal would be very unstable. So this was the Dr. Jekyll and Mr. Hyde thing, sodium ion. And so we think, okay, what metathesis reactions can take place with sodium ions? What anions does the sodium ion like? And you would say, none, right? Because all group 1 salts are soluble. Therefore, the only way to get sodium ions to react with an anion is to evaporate all the water. As you evaporate the water, you're forcing the ions together. And eventually all the water disappears and you got sodium chloride salt. You know, but they're forced together. Otherwise, they stay apart. The sodium ions stay apart from the chloride ions. So as far as metathesis goes, there's nothing there. Then we look, okay, what about acid-base? Well, sodium ions are acidic, basic, or neutral? Neutral, so skip that. And then we look at redox. Are sodium ions a good, powerful oxidizer? Sodium ions a good oxidizer? Not at all. Not at all. Sodium ions are close to par with what? What's the worst oxidizer you can think of? Lithium ion, right? And I gotta put that redox chart. You want to see what you're going to get on the test? Let me show you. You're going to, I guess I closed that by accident. You're going to get the periodic table, but just the basic one, and you're going to get this chart. This is exactly how you're going to get it. So when we look at sodium ions, very stable. You know, the only thing sodium ions can oxidize are what? The only things sodium ion, this is an oxidizer, by the way. The only things that sodium ion can oxidize are what? Calcium, potassium, and lithium. Calcium, potassium, and lithium, these are terribly unstable elements. Very dangerous. At least that's better than lithium ion. What can lithium ion oxidize? Is there anything on this chart that lithium can oxidize? No, we've hit the bottom here. There are things, but those are exotic species. Right? So sodium ion's pretty unreactive. What about nitrate? What do you know about nitrate? Is nitrate a decent base? Where's nitrate on the base chart? It's here. What do you know about here? In fact, it's so weak, we don't even consider it a base. Sodium nitrate, what do you think the pH in water is? pH 7. Sodium nitrate in water is going to be pH 7. It's because sodium ions, not acidic, nitrate, not basic. Even though it is a base on here, the only way to make it a base is to force those ions together. Okay, so we got that, and so not. What metathesis? What cations? Excuse me, this is an anion. What cations does nitrate like? Well, you know that all nitrates are Soluble, so nothing. No metathesis. Pretty much the only thing is what? So far sodium nitrate's pretty unremarkable except for its redox. And the redox is not coming from sodium, the redox is coming from nitrate, and nitrate is a decent, actually it's pretty strong, what? Oxidizer. And so sodium nitrate, this would be marked oxidizer. Why? Because of the nitrate oxidizer. And so when we're trying to understand chemical properties, it's easier to think in this way rather than in terms of an AB plus CD or an A plus BX or A plus BC type pattern. If you can do it this way, it's better. So let's go on to this one, ammonium nitrate. Well, you know, group 1 and ammonium salts are all soluble, so ammonium doesn't seem very reactive either. It doesn't seem very reactive either. But when we're looking at ammonium, okay, metathesis, no reaction. Acid base, ammonium is a weak acid. And so metathesis, we got nothing. Acid base, we got something. Let's take a look at where ammonium is in terms of acid base. Here's ammonium. Ammonium will react with all bases stronger or weaker than ammonia. It'll react with all bases stronger than ammonia. So it'll react with cyanide, carbonate, phosphate, hydroxide, sulfide. So weak acid. How about redox? Now, ammonium, does it occur on the redox chart? So let's take a look at the redox chart. Ammonium does not occur on the redox chart. So what should we say? If ammonium does not occur on the redox chart, should we just call it neutral? It doesn't want to do anything? Redox-wise? No, we can't. We need a bigger redox chart. Because this redox chart is pretty short, it's a bridge. And so we can get a bigger, but what if we don't have a bigger redox chart? Then what can we do? If we don't have a bigger redox chart, then what we can do is we can try to figure out what its redox properties are going to be like. And that is, we can do it by looking at the charges. These charges on the atom, these are called oxidation states. And we've been doing it already. Like, for example, what's the charge on hydrogen, the one you would expect? +1. That means the charge on nitrogen must be, well, if it's -4, then it would be +4, -4, which you could give it a 0 charge here. So it's actually -3. And if nitrogen's -3, then we got -3, and then we got 4 times +1. And that's going to give us a net charge of +1, which is the net charge here. And so it's -3. What does nitrogen's charge range from? Yeah, nitrogen ranges from +5 to -3, which means -3 is on the rich side or the poor side. Is it electron rich or electron poor?
Electron rich.
It's electron rich. One thing you should know about electron-rich species, like lithium. Lithium is considered electron-rich. Not because it has a negative charge, but because it gives up its electrons easily. Sodium is considered electron-rich. Sodium doesn't really need it. So if sodium loses that electron, it forms sodium ion. Does sodium ion really need that electron? Does it really want that electron? Is it going to take that electron from something? No. And so one thing is, if it's electron rich, let me give you some other examples of electron rich substances. What else is electron rich that doesn't appear on the redox chart? Another species that's electron rich is this, CH4, methane. Methane is electron rich. What is methane? Charges. These charges I'm going to start calling oxidation states. So what are the oxidation states of methane? Hydrogen is plus 1, and we have 4 of them, so it'd be 4 times plus 1. The charge is for each atom. The net charge would be 4 times plus 1, which would be plus 4. When I add up the total positive charge with the total negative charge, it has to add up to the net charge, which is 0. So I have 1 carbon, and what is the charge on carbon here? It's got to be. Yeah. And so the charge on carbon is -4. Is that electron rich or electron poor? It's electron rich. Carbon's charge varies from +4 to -4. So this is on the rich end of the spectrum. And so this is what we call a reducer. Reducers are electron rich. Oxidizers are electron poor. Well, one oxidizer is O2. O2 is electron poor. Why? Because it wants to form oxide. In this case, it's going to form carbon dioxide and dihydrogen monoxide. The oxides. CO2 and water. So this is our oxidizer here. This is not balanced, but that's it. Methane's not on the list here. And so what we're going to do is we're just going to use this type of analogy. So for example, ammonium salts burn. Sodium nitrate, you throw this in a fire, it's not going to burn. It'll cause some color because sodium ions, when they get vaporized and flame, make the flame yellow. But ammonium will actually burn. You don't want to throw this in the fire because when ammonium burns, you know what forms? When ammonium burns, will the nitrate burn? The nitrate will not burn. Why won't the nitrate burn? Why won't the nitrate burn? What's the charge on nitrogen in nitrate? Actually, it's +5, the charge. The charge on nitrogen in nitrate is +5. Can we go to +6, +7, +8? No, +5 is it. And so the nitrate won't burn, but the ammonium will burn. When the ammonium burns, what we're going to form are NOx. NOx, oxides of nitrogen, because nitrogen is a variable charge, so we might form +1, +2, +3, +4, +5. So we're going to form NOx, which are toxic. So we don't want to burn this stuff here. And so even though ammonium is not on our list, we have to watch out because ammonium is flammable. Ammonium is a good reducer. In fact, this is a very unhappy compound. Do you know why this is an unhappy compound? Because if you look at one of these nitrogens, this nitrogen is -3. In the exact same compound, there's another nitrogen. This nitrogen is +5. Wow. They're both the same. I mean, they're both the same element. They aren't exactly the same because one nitrogen ended up in ammonium and it ended up very rich or very poor. One nitrogen ended up very rich. The other nitrogen ended up very poor in the same compound. So one nitrogen is very rich, the other is very poor, but they're both nitrogen. If one nitrogen got in a tug of war with another nitrogen, which nitrogen would win? aren't they the same element, right? And so do you think this is a stable, happy compound? No. And so, even though that's not on the redox list, this, I'm going to show a little video on this one. Have you heard of Texas City? Texas City is the home of the worst, a couple of the worst industrial accidents in the U.S. With Texas City, the first one being the worst. We'll watch Texas City.
Much time in Texas City with all the big ships that come and go, the oil and chemical refineries, the pipelines and storage tanks brimming with flammable products. You can't spend much time here without thinking the unthinkable. Could it happen again? Could Texas City be another boom town in the worst possible way? Years ago, Texas City burned its way into the nation's conscience. The worst industrial accident in American history made Texas City synonymous with disaster. The day it happened, Will Lane was very near the epicenter.
It was very strange. I'm really glad to be alive.
Lane was a young chemist at the Monsanto chemical plant. He remembers seeing the bright orange smoke from a burning ship. Firefighters were busy pouring water on the French freighter Grand Camp at the city docks across from the Monsanto plant.
You could look at it, it's real pretty to watch. And there were townspeople by the hundreds that lined the part of our parking lot that was nearest to the ship. They came down to watch a fire.
Texas City had a new fire truck, and this was its first day out. 27 firemen were on the docks trying to put out the fire. The burning ship was so hot, the water around it was boiling. But as a chemist, there was something about that orange-colored smoke that worried Will Lane.
We get to see bits and pieces of paper bagging going up in the air in a wave. And my boss thought, and I thought too, that we were witnessing a nitrate fire. But someone had said, it's a grain ship. The grain is on fire.
So believing it was only a matter of time before the fire was out, Will Lane went back to work at the Monsanto lab. But the fire was growing hotter, and the orange smoke was attracting an even larger crowd along the docks.
It was a very, very strong sulfur in the air, sulfur fumes.
Herb Metzger watched the fire while talking to a group of high school kids.
This smoke was just a beautiful orange.
Mary Hunter, a Monsanto secretary, was watching from her office window. And across town, Mrs. Knappenberger, a housewife with a home camera, came here to the Texas City dike to get a closer look at the burning ship. She didn't know it then, but she was about to record America's greatest man-made disaster. The ship had been loaded not with grain, but with ammonium nitrate fertilizer, the same ingredient that would be used years later in the Oklahoma City bombing. The Texas City blast was so strong it registered as an earthquake in Denver, 900 miles away. It created a tidal wave that washed a barge into a parking lot. 2 airplanes circling the ship were blasted from the sky. Flying debris punctured chemical storage tanks, creating an even larger inferno.
We have another truck up here off of the road. It had about 10 or 15 men, and they were all crushed.
The explosion killed at least 581 people, including school children who had come to watch the fire. But the danger was far from over. Tomorrow, we'll hear the stories of survival and courage from the people who were there 50 years ago. Charles Hadlock, 11 News, Texas City. This is Charles Hadlock. Texas City has tried to outlive its past, but it's hard. There are so many reminders. An anchor here, a propeller there, and sad, sometimes painful memories all around. Even today, 50 years later, the tragedy is not forgotten. 6th Street, the once busy main street of Texas City, has been renamed the Street of Memories. For it was along this street that so many screamed and ran for their lives. The explosion of the French freighter Grand Camp left an entire town dazed and confused.
ran as fast, as hard as I could.
There are many stories of survival. Dr. Will Lane was in the Monsanto lab. He had been watching with suspicion the bright orange smoke of the burning ship docked next to the plant when it suddenly exploded.
And when the lights just went out, I could not see more than 2 or 3 feet. And I thought, my God, it was a nitrate explosion. I'll probably lie right here and be burned to death.
He got up, looked over his shoulder at the burning tanks of benzene, and ran for his life.
Passed a car in which 2 people had been decapitated. Then I passed one of the 2 little planes that had been flying around overhead, came down along the path that I took up to the town.
I'm sure all of that glass came into us, and I must have gone like this. And so my arm was injured all in here.
Mary Hunter was also in the Monsanto plant. To this day, she still has shards of glass in her body.
I had it cut out of me, but luckily it had lead in it. And therefore when they x-rayed it, they could find the glass.
Before the explosion, hundreds of people were on the docks, including Herb Metzger.
I had turned to walk away. I had my back to the explosion, but the force hit me in the back, and it sort of just, I don't know, I would say it picked me up, but it moved me forward 20 or 30 feet.
Suddenly, pieces of the ship were falling all around him. He crawled under a car.
A couple of pieces hit the car. I could feel it, you know, when it jarred, but nothing hit me.
Here comes another explosion. But pieces of metal did hit the High Flyer, a second ship loaded with ammonium nitrate. Efforts to tow the burning ship out to sea failed, and 14 hours later, it exploded. The fires burned for days. Nearly 600 people died, and 5,000 were left injured or homeless. Those who survived helped each other.
We had to pry some folks out that had telephone poles, in fact, I guess, or some kind of big poles blown across them. They obviously were crushed, you know. It was not a nice sight, but kind of steeled myself to it for a while.
Even after the dead were buried, many survivors never talked about it again. But over the half-century since the explosion, they rebuilt their lives and their city. That must have been a hard thing to do, with so many memories around. Charles Hadlock, 11 News, Texas City.
So yeah, this is bad because this has an oxidizer here, nitrate, and a reducer in the same compound. Sodium ion, although it's an oxidizer, it's so weak we don't even worry about it. I mean, it's just too weak. And so this one is just an oxidizer alone. This is both. And so what we want to do is we want to at least think about properties in this way. And so let me finish off with this one. HF, what do you know about HF? Is a weak acid, strong acid? HF is a weak acid. And then we have acetic acid. Is that a weak acid or a strong acid? Hey, both of these are weak acids. Have you ever spilled acetic acid? Have you ever spilled vinegar on your skin? It may cause a little bit of irritation, but do you worry about it? No big deal. And so HF is also a weak acid. Let's see, in terms of strength, where would HF lie? Let me just take a quick look at our chart here and see where HF lies. It looks like HF is a little stronger than acetic acid. Do you see that? HF is here, acetic is here. Not that big of a difference. HF is stronger than formic acid. And so maybe HF is a little bit more hazardous, but still they're both weak acids. Have you ever spilled hydrochloric acid on you? Hydrochloric acid is a strong acid. I've spilled lots of hydrochloric acid on me, and it depends on the concentration, but it's not that big of a deal. Some people are more sensitive than others, though, so you want to avoid it. But if you treat these two acids the same, then you're in trouble. you wouldn't treat these two acids the same because it's not the acid properties that are worrisome. Like, for example, you could eat this stuff. You know. Actually, the acetic acid, just for your information, burns. You know. When we look at the carbon here is -2. So it's kind of electron rich. So acetic acid burn. This one is not. This one you can't burn because fluoride, even though it's -1, doesn't want to lose an electron. Fluoride doesn't burn. But that's not it either. It's not the redox properties. It's not the acid-base properties. You know what makes this acid very dangerous? There's no way I'd ever want to spill HF on me. No way. Because HF has, well, if it's not redox, and it's not acid-base, then what is it? It's metathesis, you know, and metathesis is fluoride will precipitate out with calcium in your bones and cause severe pain. And I've heard, you know, it's so bad, many people, not many, but people have died from HF. And so let's take a look at HF burns. Actually, you don't have to look at these. These are pretty gruesome. But if you want to see what HF burns look like, okay, well, there you go. Not bad. Not too bad. This is not because it's a strong acid. This is because of its metathesis properties. I mean, these are like straight out of a horror movie, but these are real. Maybe, I don't know if that's real, but that's, I don't know. I mean, they don't look like they're in too much pain, so I don't think. But some of these are real, for sure. I mean, and are nasty. When you spill vinegar on your hands end up looking like this. Not even close. And so we got to worry about all the properties. A lot of people, we only worry about the acid-base properties, but they do this in the movies because HF is used to get rid of bodies or something in those crime movies, right? I think HF was used in the but a lot of these are real. Sorry, I didn't go through and look, but I think that one's real. This one for sure is real. This is skin graft there. Yeah. HF nasty. Okay, that's it.